Zertifikat, das ich geholt habe, es dann noch vorher holen. Das kann nicht ganz alle verwünscht.
Ja, aber ich bin ehrlich, das geht bei mir jetzt gerade hier rein und raus, weil das ja.
If you could all have a seat, please, that would be great. Starting in a minute.
Hello, everybody. There are still seats available in the front row, first row.
It's the Swiss phenomenon, I guess, yeah.
Du hast den Pointer, ja. Genau. Nee, okay, würde ich sagen. Legen wir los.
Let's go.
Okay, in this case, let's start it with the result presentation and more or less the highlight of a 2 days event, which was prepared more or less the last 11 months with all of us, Opendata.ch, High-Tech Zentrum, the challenge owners, many people around. So first of all, a big thank you for all of you who made this event possible with the support upfront during the event, sharing ideas, working the 2 days on the challenges. Also big thank to the FHNW, our host, the flexibility. Christoph, a big applause for your ICT. You're pretty flexible and made it all possible. And now also a big thanks for the partners, and for the first time you see that we changed agenda, the venue slightly compared to the previous 5 years. So we also have booths from the partners. What else? What else do we have? Only one screen compared to the last years, and what else? A live stream. So just in case, I sent most of you guys, I have in my phone the link via WhatsApp and via SMS and what else, so that you just can forward it, just in case you have friends, colleagues, who else who want to join or want to see the challenges and the results. So a last minute idea from Oleg and Florin, who made it also possible so that you can stream it, we'll also record it.
Yeah, and it's also going to be a lot, right? So if you miss something, it's also possible to rewatch the presentations afterwards. Perfect. If you want to, well, all right. If you want to, can't say tweet anymore, but if you want to post on social media, use the hashtag ETH24. Please feel free to tag our respective organizations. We're also very much looking forward to your feedback on the whole event. So if you would mind scanning the QR code, you can give us feedback via Typeform. You'll also get the link again via after the event via email. But also maybe if you're on the way home and don't have anything to do, you can already fill it out. Yes, and now we're getting into the fun part, the presentations, the pitches. If group one can already prepare themselves, make yourself ready, that would be great. I'm going to call you up in a minute. Again, the rules, know your slot. So we're going to go in the same order as we did on the first day yesterday. You're going to have 3 minutes on stage. We're going to try to keep the time exactly. and have fun. That's the most important rule, I guess.
We are freestylers today, and said, okay, Oleg is taking the time. We said 4 minutes plus Q&A. So more or less, let's say 3 minutes pitching plus minus, and then also Q&A from the audience is welcome or are welcome. So if you have questions to the team, please don't hesitate. Also ask them, so that we also can interact with each other.
Yes, and with that being said, group number 1, please come to the front. It's your time to shine. Eh?
Okay, so thanks a lot. This is the presentation that we are going to do. This is our team. We were 3, and we had to do a real visualization that show consumption in real time. So the goal, basically, what we wanted to avoid. What we wanted to avoid is high peak of consumption, because this is highly cost. There is a high cost, and this is very inefficient. And we also wanted to show the consumer consumption and also the grid consumption, so that you can say, okay, now there is a peak in grid consumption, and I don't want to also consume and overload the grid. So the goal was to avoid these peaks, but how did we measure the peaks? And we basically created a threshold. Here you have the mathematical formula, and we say, okay, if it's above this threshold, we make the difference between the value and the threshold, and we can also measure. And then we can have a correlation between the consumer distance above the peak, above the threshold, and also the grid one. And here we did like a web app visualization. So yeah, about.
So our web app is divided in 2 parts. The first part is to see the grid consumption. The main elements are an alert if the grid is going to a peak, like the closeness to the peak, to the previous highest peak, and how much the current peak is costing the grid provider. And the second part of the visualization is for each individual household to see their consumption and their correlation with regards to the peaks in the grid. So are you, as a consumer, contributing to creating peaks or not? And then some alerts and the current price that you pay depending on your consumption. So we have some alert system depending on the state of the grid and your consumption to reflect and give you tips to what to do. And that's basically it.
It's me? Yeah. So let's talk about chickens. Okay, so chickens. So we will also playing with some gamification for the dashboard for the household energy consumption. So you can go there and check it. So we just describe like in real time, but it's fake real time data. So you can navigate how much your home is consuming, and also you have fun calculator how to calculate your energy consumption kilowatt. So basically chickens. Chickens are dinosaurs, and big dinosaurs died a few million years ago. They were turned into fossil fuel, which we are currently using to generate energy. So chickens have also kilocalories. So kilocalories, it's the same as kilowatt hour. And chickens are some smaller than dinosaurs, but we can interpolate them to dinosaurs. In this case, we can measure dinosaurs in kilocalories. And kilocalories is the same as kilowatt hours. So you can go there, put your kilowatt hours, and you will see how much dinosaurs bodies are you using to generate your energy for this month, and maybe be more conscious because these dinosaurs die for us. Actually, it's not dinosaurs, it's kind of cellulose, but.
No, I won't raise a question about the chicken and the dinosaurs. No, for me it's important. All I wanted to ask, first of all, thanks a lot also to Ben, who made it possible, also to brought the topic in, and then of course to the team. My question would be, what was the biggest challenge in this during the last 1.5 days? The biggest challenge in the challenge? To find the chicken, or to define the dinosaur, or?
No, I think the biggest challenge was the first question: how do we define if it's a peak or not? Okay. And yeah, we took us quite a long time. Yeah.
So is the technical solution in the documentation?
Not yet.
Okay, cool. Just any further questions from the audience?
Thank you. Very interesting. I like the graphics. My question is about the application. So you want to give this to end users, to households, but what is my motivation? Because in Switzerland there is no dynamic pricing. I do not save anything. How would you stimulate me to use this?
So the idea was more to have transparency for the end user, because they don't know how much do they add to the grid costs by creating peaks. And while we are not allowed to have really dynamic pricing in real time, we are allowed to have real-time transparency for the end user. And you could just show, hey, if you could now stop charging your car, just by visually looking at, should I do this or should I not do this, you could reduce your end user costs just by voluntarily stopping to put load onto the grid. And the next step is, okay, this is a voluntary action. You could turn this visualization into an API, and you could connect your home control to it, and you could have an automatic decrease in grid load.
Guess also maybe interesting for utilities who need to find some solutions or need to provide some solutions, and getting an idea of how to implement it.
It also works in the smaller scale. If you think of CEF or LEG, they might be under peak pricing, and you could use this tomorrow. I mean, the code is online.
Further questions? If this is not the case, then the team, thanks a lot.
Thanks to the team. Great work.
In this case, team number 2, What's and Bots. Angelos, where's the team left?
Where's the team? Do you want to stand up? Okay. Yeah. I will do it on my own. Yeah, so our challenge, just to quickly remind you, was to generate a generative AI solution. So to ask something like ChatGPT to provide us with detailed electricity prices for different providers across Switzerland. These are, we had quite a big team. So exactly, the motivation behind this is that we need this detailed breakdown of the different products so that we can, for example, calculate more precisely the economic viability of new business models, or study more precisely energy efficiency measures and so on. And what we had in mind, we already had a pipeline which got to the different PDFs of the different providers and got the text out of it, and we wanted to use Gen AI to get the different breakdown of the different products, electricity and grid products. So how we started? We started with a very big and very precise, very complicated schema of data, so data structure, and with a very small and simple prompt. So what we said to Gen AI was, take this structure and fill it up with data you find in this PDF. And this doesn't work very well. So we moved to a different approach. We tried to explain as much as possible to AI what the products are, what the structure, what the data we're giving them is, and how they should process it. And we tried to make the JSON schema as simple as possible. So we run some tests on it. It's not completely successful yet. So we managed to get out of 75% of the people we tried it for 125 providers, and we managed to get numbers from 75% of them. 33.5% of them were more complete, but validation, everything failed until now. But we have some ideas on how to improve things. Here is also a front end we built so that we can quickly see if the results are correct or not. The main learnings are that the main challenge was that the different PDFs or different providers have a different structure. People are very creative. Yeah, it's a challenge. So we need to enhance, we need to explain exactly what we want to have to AI, and we also need to have a balance between abstraction and preciseness, both in the schema and in the prompt. There are a lot of things we can try to improve. I won't mention them, but maybe there is a much quicker way to get what we want is someone please publish the data. The data is somewhere. We don't need to use GenAI to get the data. So maybe this is the best way to solve this problem. And this is a QR code of a live demo you can try. So you can see, you can choose your own provider, and you can see how a live run of the prompt and how the data are, how we get the data from OpenAI. Yeah, thank you very much.
Very cool. Big round of applause. Any questions for the team? Yes.
Is EKZ publishing their tariffs over an API?
Yes, of course, of course.
Perfect.
Yeah. Oh.
Further questions? Then allow me one question from my side. The cooperation GeoImpact EKZ, will it be continued?
Yes.
Also, will you also make use? I mean, since EKZ is a long-term partner, and I know that you also continue with the work and the outcome. So when can we expect the product?
Yeah, we'll have to make a debrief, see what we learned, what we can improve from it, and in the coming months probably.
Keep us updated. We need also success stories.
Okay.
Angelos, thanks a lot.
Thank you very much.
And to the EKZ.
Thank you.
All right, challenge number 3.
We have to really hurry because we have 14 slides. I will go through it. That was our challenge. We had to find a model. The problem is we have some instability. We have to stabilize. What was the objective? Was the secondary Regelenergie. And these are the fields which we received from the CSVs.
It seems like I got the harder part here. All right, yeah. So we got a lot of data, timestamps. That prediction target was activated balancing volumes from the secondary reserves, positive and negative. And then we got production data, we got consumption data, border flows data, time information, net transfer capacity, and so on. And we mostly looked at time features, so kind of seasonal patterns, daily patterns, hourly patterns, weather-related data, and cross-border data. Here you see some feature importance, and what you see already on the top is hour, minutes, is the first two, weekdays, fourth, season, month. So kind of features that are related to time are very important. So what we first started with actually is understanding this time-related patterns. So what you see here on the x-axis are hours of the day, and on the y-axis the days Monday to Sunday. And that's a heat plot with the average positive activation. And what you see here, this kind of brighter part, Monday to Friday, it seems like in the morning hour you have an average higher activation values. Similarly in the evening hours, and what is also interesting that on the weekends is very bright too. So you have some kind of strong patterns over the day and over weekends or weekdays. This is maybe a bit more advanced. I'll skip 1 out of the 14. So this was a quite interesting insight actually. So if you dig deeper into this time patterns, then what you see, so the blue bars are the positive and the red bars are the negative activation, the average values. And what you see is if you start with the first hour, is you have kind of this from up to down patterns. And then in the second hour, you have it again and again and again. So it seems like on average, you have more positive activation in the first quarter, for example, and much more negative activation in the last quarter. And interestingly, this type of pattern switches over the day. So if you look carefully, then it's not kind of this downward shaping slope, but becomes an upward shaping slope around like 4 or 5 a.m. to 7 a.m. and similarly in the afternoon. And what you also see in red is the price data, and there seems to be some kind of dependence. So our assumption is that maybe it has to do something with the ramping of the production. All right, so then okay, time is over. So you can predict something and that's the end.
Maybe we use the last time of then we raise a question. What would be the expected prediction? The last slide. Short-term forecast. How would it be if you use the time in this with the question?
Well, so as you see, you get some kind of pattern, but obviously it's very difficult to predict these extreme activations. So you have kind of this low signal, so you have this reversion to the mean phenomenon. So one approach could be to try to estimate quantiles instead of means. Yeah, and of course incorporate more features.
Okay. Questions to the audience? Allow me one last question. Your recommendation to the challenge?
Yeah, maybe just to add from the Swissgrid control room, this is a pattern we observe every day when the hydropower kicks in the morning and goes out at lunchtime again and kicks in the afternoon or evening again. So then we have this live balancing activation graph that shows exactly what you've been showing. So it's definitely, your assumption is right, it's the hydro production kicking in and out in Switzerland.
Okay, then the follow-up question for me, why can't you get rid of that in a quarter-hour basis on the market?
It's because the plant needs a certain time to go up and down, and this ramp is not really considered in the schedules because the schedules just are like the second it's the full hour, we assume the position has changed, but in reality they take like a few minutes to go from 200 megawatts to 600 megawatts, and these deltas are then causing these activations.
This will be also the challenge Gilles and her team needs to solve and try to implement in cooperation with Swissgrid and also the team. Thanks a lot. Mr. and Mrs. Refrigerator, team number 4.
Thank you. All right, I have the honor to present our team. So those are the survivors of the first day. So this picture was just taken earlier. We have been more, but those are the strong. So our challenge was about rewarding households for saving energy with an open data approach. And we first tried to divide our group in subsets. We divided it into 4 groups, and we want to do one group for analysis and research, one group for data engineering, one for data science, and one for web development, web application. So the first group just focused on gathering the data on the topic in general and then identify the options we want to implement. The data engineering group focused on building the data set and clustering it, for example, to estimate the energy consumption based off indirect features, for example, volume of a fridge or the age of a fridge. Then the data science group focused on analyzing or identifying what kind of old fridge you have. There we had 2 methods using GPT models and another model who used data manuals, user manuals with text-to-image processing, and we implemented actually both. And finally, we wanted to build everything into a web application, and that's what we are seeing later on. So first of all, what are the most important users of these applications? We found that around 36% of all households in Switzerland are own property used by their own properties, and the rest is nearly tenants managed by property management. So this is the way more huge group. And finally, if you want to replace your fridge, you have to ask the tenant. So yeah, that's the big issue we have to address here. And finally, that's why we have to motivate the tenant, and there are some regulations in place. For example, we can show the CO2 and make it more visible for the end customer, which is the most green tenant, for example. So to data engineering, we had about like 40,000 fridges we analyzed, and the most important fields were like volume, consumption per year, and market start date. And the idea was to cluster them by volume, calculate the average per year, and use this to indirectly determine the fridge consumption. The problem is, you see on the left, you see that there were nearly no fridges before 2022. So, yeah, you have to make the assumptions. So, yeah, let's linear interpolate it or extrapolate it in this case. And you see from 22 to 2024, for all clusters, the energy efficiency increases. Yeah, then you can do this backwards or forwards, whatever you want. So that was our solution design for everything. So we had a front end built in Angular. It was hosted in Replit, and then we had like 2 options which could be chosen in the front end. You could go option 1, where you take just an image of your fridge, of your device. Then we do some prompt engineering, accumulate the image with like the data I have shown, and then we give it to the GPT model, and then you get back your energy consumption. The option 2 is we go to our Databricks environment, trigger an ML job, do some image-to-text transformation, text refinement, put it into a model, ask a database, is the model in there, and then estimate the energy consumption by this. So this is a short demo of the interface. We have the landlord view and the tenant view. You can add a device. The video is playing. I cannot stop it. There you can take your image. You choose your user manual, and yeah, it's not connected, but I show you how it works later. I'm fast. You can upload the image. Now it's going to the OpenAI API, and then you get back your answer. Hooray! This is the text to image. You can upload your manual or an image of your manual. That doesn't matter. And then you get back your model, and in this case, the energy efficiency class. So that's it.
Thank you.
Thank you.
Questions for the team? No, doesn't seem to be the case. So what's next for Mr. and Mrs. Refrigerator? What are you going to do with the results?
Yeah, fill all the gaps in the data, of course. That's the main issue. We don't have that much to make a very accurate estimation. Though that will be the issue, to estimate how much of an inaccuracy is it actually. and then refine it to a sensible application, like in the shop context, where you can actually compare it to a new device and make a business model most likely out of it.
Cool. Yes, a question.
I probably missed it, but why didn't you have any refrigerators before 2020?
There are, but not that many. And that's just in the database. It's like the database.
That was the data you had? Okay.
There are, but it's then not usually with annual energy consumption. And you have to accumulate a lot of different data sources, and that was way too much for those 2 days.
Okay.
So we just focused on this database and built up a very simple model. So.
Okay, good invention.
All right. There seem to be no more questions. Thank you very much. And up next is group number 5.
I'll do the talking.
You'll do the talking, you do the clicking, okay.
So this is our team, or most
Product
of it,
placement.
challenge owners missing, one of them. This is our challenge number 5, the impact of logistic truck electrification and electrical infrastructure. The challenge was to assess the impact on the grid if all of the trucks from this one distribution center would be electrified. The data we got was the weekly operating schedule of about 160 trucks from a Coop distribution center. How it started, we looked at the data to see what we can learn from it, translate named locations from the shops into coordinates, set up a local open route server to circumvent the API restrictions, which enabled us to also make nice spider graphs of where the trucks are headed out, with the addition of the frequency, or how many trucks are taking what route. And you can see highways are more likely to be used than any other roads. Then we looked at the distribution of distances, if it is actually possible to electrify those routes, and we can say yes, because a lot of the daily routes can be electrified with truck with ranges of 200 kilometers, but we have not checked if any one truck is taking a route of 200 kilometers most of the days, but has one day with an extra long route, which then would complicate things. We looked at the distribution time-wise. They all have a quite early start, around 4 o'clock in the morning. They do, most of them do 2 tours per day. You can see 2 gray areas where they leave and the orange areas where they come back. And you can see the distribution of different length of the tours. So some of them come back quite late. Then for the summarized usage, this is where we run out of time because of issues with time series and or time data types mostly. On average, it is around 40,000 kilometers driven every day by the trucks in these fleets, which equals to around 55 megawatt hours of energy used per day. And if you have a very conservative approach of charging from 10 p.m. when all of the trucks are back and we have low tariffs until 4 a.m. when most of them leave again, we need about 9 megawatts of charging power, which is way too much as the feedback from our challenge owner. So the idea is to have not the green area, but more of a bluish. So to start earlier in the day, maybe start even throughout the day if the trucks are back and be unloaded and loaded again. So this is the outlook, what we wanted to do, or maybe will continue to do. And intelligent charging is needed. These graphs are from a similar project where you can see that it is possible to more than half the power needed to charge. I think this was public transport vehicles. Yeah, and this is what Severin and the Hasalu will work on for another 1.5 years for the question if we will continue. Well, we probably won't, but it is an ongoing research project. That was it.
Thank you very much, Bill. Allow me the first question. Since I also designed the project a year ago, I'm pretty keen on the message. I mean, I know Severin is working the next 1.5 years on the project together with the project partners. Your message and also which information is still required so that we can also ask for co-op and the grid owner, which would help. So far we, or the team received the logistical data, etc. But is still also data missing, which would it make easier, or is it just the process and the ideas of how to implement it and how to use it?
Now we had planned schedules, so what would be interesting would be real-time schedules. Like if the trucks are all arriving too late, then you would make assumptions which are not applicable to real-world causes. So I think real-world data would probably help to be sure that whatever you planned theoretically would then also work.
Okay, it's planned versus real data, because it was also mentioned during the meeting, saying, okay, there's a gap, but okay. Questions from the audience?
Hi, Andreas Primeo. Just a remark, not a question. It would be interesting to see how dynamic pricing would influence the planning of the day ahead routes.
Well, I think the route can't be changed because you need food every day. But we thought of changing the charging schedule with not only make it as little peak as possible, but maybe there's business models with, well, if you use less power during the evening peak, say from 5 to 7, we'll give you some free peak power during the rest of the night. But then this is for the challenge owner to figure out. But yeah, it would be interesting to kind of see how much would be possible or how big of an impact. If you only save, I'd say 100 kilowatts of shift, you wouldn't care to put in any algorithms. But if you can save quite a bit, that sure would help. Yeah.
Thank you. Did you look also at what if the trucks would charge during the unloading and loading?
We looked at that some of the trucks have their mandatory break times out in the field as well, but this was not in the schedule, or it was not as data in a schedule. It was just notes on the big plan, which was not as a handlebar with just manual edits. But yeah, it would be interesting to get it charged because they often have breaks at co-owned locations as well, where they could install their own chargers. Yeah.
Further question from my side, are the trucks usually going the same paths every day, or is this like changing dynamically, at least on the plan? I guess in real life it's probably changing again, no, but is it like the same path every day for each truck, or is
no,
it
it's a weekly schedule, so
okay.
It's a 6-day schedule, but this one is done weekly. And I think you have some similar patterns more than once a week, because I think there's 2 or 3 times where every shop gets its delivery, but not necessarily on the same route or the same truck.
All right, thanks.
Very short question. How about the charging mode? Is it only single direction, or it can be or considered to be bi-directional?
We would only look at unidirectional charging first, because you use all the energy. Maybe from Saturday evening till Monday morning, you would have some time to play around. Otherwise, we're already quite limited with just getting enough power into the trucks, so there's no time to spend energy flowing out again.
Okay, and the charging modes, have you, or is that part of the plan to consider only the faster charge, slow charge, or like how to different charging speed?
No, we haven't looked at it in details. So the limit we would say is fast charging every truck because often there is very little time and you gain a lot of flexibility, but it costs some more.
Yeah.
So there are quite a few routes with less than 100 kilometers where the truck is around more often. So probably you could go for slower, fast charging for certain trucks, whereas you need faster for some others.
The last question to this challenge.
Did you consider batteries or stationary batteries to buffer the power?
No, we haven't looked at any of those details yet.
Okay.
So there's also the question of if there's PV on the rooftop of the distribution center, you might really want to have the trucks back throughout the day for maybe an hour longer or something to use all your own provided energy, but we haven't looked at details. Yeah.
Okay, thank you.
This is part of the remaining 18 months. So this is just to get the data, design it, and to see what could be a possible solution for the on-site logistic hub. 18 minutes, yeah, exactly. Thanks a lot, Bill and the team. And with this, I would like to hand over for the next challenge. Planeto, Jonathan, and team.
Click. Thanks. Yes. So, just wait for the team to come up. So our challenge was very theoretical, let's say, looking at applying graph theory in district heat networks. Here we made sure to get a picture at the beginning when everyone was still fresh. I have another one after, but I thought, it's not quite as good. So what we did was split up into different groups and basically brainstorm a bit some different approaches. We spent some time really understanding a bit the theory, understanding a bit where the theory and the practice meet. We had a couple of methods that worked out, actually started to give us some optimized results, which I'll let the team members introduce the ones that they each worked on, and which is this augmented minimum spanning tree, shortest path, which we call Doge stick retrieval, for reasons you'll see in a minute, and also a weighted distance matrix, and as well as some methods which we tried, but like any scientific work, they didn't quite pan out. One thing we had also in common, of course, across all the groups was to define a common cost function, so that would apply across the different kinds of optimization. So the first one, I think I'll hand over to Tyler.
Yeah, cool. So we had the good fortune of starting with a minimal spanning tree algorithm provided by Planeto, which was really helpful in kind of getting us started understanding the theory. One thing that we thought might be interesting is just to start from a minimally useful and workable case in which we minimize the distance between nodes, and that's what the minimal spanning tree accomplishes. And we basically said, okay, let's just perturb one edge at a time and see if we can achieve a lower cost function than what we started with. So in the end, we were able to achieve a 33% reduction, but there's a few questions remain with this method.
Yeah, the second method that we tried was switching away from the paradigm of shortest path, going towards shortest distance to the consumer of the energy. And as you can see, it reduces the cost at an increase in the length, but luckily this is all underground, so you won't see this mess.
Then we used a weighted distance matrix where we used the consumption as well as the distance, and then we put in the MST. And we can see on the left that it goes all the way around. Here we split at the origin, so uses the consumption and tries to divide. So it was quite useful for certain cases.
And we also tried experimenting some different approaches. So one deterministic approach to try and adapt is that it? That we tried didn't quite work out because there wasn't necessarily significant improvements over the solution, the base solution. And also we brainstormed, or we attempted, one group attempted quite a few different approaches, genetic algorithms. One of the main challenges there was that generating initial solutions was then challenging to solve the flows through these networks. And so you would actually need a better flow solver to maybe be able to try more complicated network topologies that would be generated. And we also tried a few other, which for interest of time, maybe I'll stop there because I see you looking at me. Thank you.
All right, thank you. Sorry for the mean look, right? Yes, questions from the audience, yes.
Did you consider reliability at all? Because I saw in the different topologies you had like very different dependencies of the different heat sinks from one or two paths. So if one path fails, like many heat sinks are not connected to the network anymore.
So actually this links to this challenge here with the genetic algorithm. So the solver we used for the networks depends on an acyclic graph, so a graph with no loops in it. This is a bit of a limitation. Actually, we have a more elaborate solver, but it requires more prerequisites to apply. Because normally what you would do is build in some loops into these networks that there's kind of redundancies in pathways. But these are always pure tree networks, so there's actually no redundancy, so reliability could be an issue. But we need to bring more elaborate solvers to actually address this problem.
Yes, one more question.
Thank you. You showed on the picture that you have roads and stuff like this. Isn't it cheaper to dig a tunnel under a road than under a house, or does it matter where the tunnel is?
I was hoping no one would notice that. So this is actually a simplified view. So and this was a big part of the understanding we had to build within the team. What we have is graph edges, but actually that represents road sections. So although it's drawn as a single line going from one building to another, it's actually internally representing a piece of road that would then be connected. So the data associated with that edge is actually a road data, but the way we draw it on the graph is just a straight line, just for prototyping, basically.
Yeah. Okay, thank you.
There doesn't seem to be any more questions. Then again, a huge round of applause for the team.
Thank you very much.
And next up is challenge number 7, team number 7, Axpo and CKW.
No one else wanted to come here, so here I am. So I'm going to try and be quick. Let's see if I can manage. Our challenge was to take simple smart grid data and try and cluster it, and you can see that we got so good at it that we even clustered ourselves when we took this picture. So our starting point was a simple CSV file which had 3 components, a unique ID for every household. There were about 9,000 of them in the canton of Lucerne. Then we had timestamps in 15-minute intervals, and then we had the demand in kilowatt hours. So first we got on to cleaning this. It was actually a really big amount of data. We had to reduce it because we didn't have any special cool servers available to us. So we reduced it to about 1,800 IDs, and then we also filtered out infrequent consumers. Good, and then we started building up a features list. We enriched our data with, for example, weather data, temperature, and sunlight, and also the holidays in Lucerne. And then we also started transforming. We got some averages, some maximums, some standard deviations, you know, that kind of a thing. And then we started clustering it and got many results. So, first lesson, don't cluster everything. You won't find anything. Then this is what you get when you look specifically at the weather. So we have temperature and sun, and we are measuring it against the mean consumption. you see these, oh my God. We also created these tables where you can see that different households move clusters throughout the seasons, but sometimes they don't. It's quite rare. This is an interesting graph looking at the change in demand. In comparison with the standard deviation, we see that we have some low variance households and some high variance, quick changing ones. Then we got some funkier stuff that looks like this. And when you look at it over, you can look at these clusters and see how they consume differently over a 24-hour period, which looks very cool. What did we learn from this? Is it would be nice to have a server like Databricks, and features are nice, but you kind of want more of them. Less is more. Sorry, that was the wrong thing. I'm out.
Fiona, thanks. Thank you very much. And also, I would ask for a second applause because she was here alone. The team is sitting over there, and I will put the questions and all the audits to the team and to the challenge owner. Fiona, thanks a lot. Any questions to the team?
I might have to pass them over, but...
Yes, the question is for CKW. Do you plan to publish any labels on your data? Because as grid operator, we know, of course, more about those profiles than we publish. So what's the idea?
It's not planned, but why not? If we find some interesting labels, yeah. Also labels, you mean the
you have some characterization of the customers,
yeah,
right?
The clusters we find. It could be feasible, but the good thing is we have now it all on a Git repo, so you can build your own clusters.
Okay.
So you mentioned that you used or you fetched, I guess, from different data sources. In this case, weather data. So did you use like actual data that occur at the same time as the measurements?
Yes, we had historical, our smart grid data was historical, and it was labeled with timestamps, so we went and found weather data of the corresponding years.
Okay, thanks.
The resolution wasn't as high as our smart grid data.
But it
so
was
we
actual data, not typical meteorological data.
Yeah.
Okay, maybe a quick follow-up. I missed something. You want to cluster the consumers, right?
Yes.
So why do you need meteorological data for that? Isn't it just about the consumption
because
itself?
Consumption is theoretically correlated with weather. You need more heat in the winter, and also the smart meter only measures how much electricity is being taken out of the grid. If among these IDs, some of these households have a PV system, they would be consuming less during high sun periods. Does that make sense?
Further questions?
If you had such an issue with a big number of features, did you think about doing any dimension reduction before you applied the clustering algorithms?
I'm seeing nodding, but I think someone else should answer this.
Yeah, in some approaches, of course, we used dimensional reduction like PCA and others.
But I mean, before you applied the...
Before we did the cluster, yeah.
Okay.
Yeah.
Okay.
Also TSNE we used, of course, yeah. UMAP. We tried different ones, yeah.
Further questions? One last applause, Fiona. And here I would like to hand over to Christoph and the first Swisscode challenge.
Thank you very much. All right. So our challenge was about forecasting the PV installation angles. And right at the beginning, I gave both teams the task to assign a speaker. I would ask both speakers to come on stage. I hope that works properly. All right. In the meantime, I'll quickly reintroduce the challenge. We don't have slides. I will comment on this in a second. So the challenge was predict the PV installation angle, which is the orientation and tilt. So orientation is where the panel faces, and tilt is how much it's tilted against the sky. And we have some testing data that we don't fully trust, and the training data is from Sonnendach, which has the installation, the roof angles, and the essential details on every building. And the task was from this data on buildings, on roofs, could you predict the installation angles that people would choose to put their PV plants on? Yeah, and the idea was originally to have more of a, let's say, not really a competition, but it turned out to be a pretty tough competition in the end. So you see up here, essentially, for the orientation data, I'll have to improvise a little bit with the laptop, but the top plot here shows the orientation fight between both teams, so to say, over time, and especially at the end, you can see that there's been quite some fighting between both teams. Similarly for the tilt, where you can see a little bit more of a convergence in the end. And yeah, the best part of everything is that we have two winners. So one team outperformed the other in orientation, and the other team outperformed the first in tilt. So everyone won, and we are happy to hear your insights into the data. One more detail from my side. So just to give you some detail on the scores, did you see here? This is essentially just the two norms of the orientation and tilt errors that were produced between the test data and the data that was submitted. And the baseline model, which is oriented south and has like a tilt of 30 degrees, is roughly 2,200 for the orientation, and it's roughly 600 for the tilt. So there was some improvement, and we will now have some insights as to how this improvement was achieved.
All right, so you already can see different working modes, so to speak. So double diamond, problem space exploration. What do we want to do? Do we want to provide Swissgrid with a sensible solution? Do we want to win the competition? Do we want to lose the competition, because then we might not have to present anything? Well, we tried to win, but someone with this amazing infrastructure decided to limit brute forcing and submissions by 3 minutes every submission every 3 minutes. So yeah, well, we had to put in some work until the end, and I think both teams started to brute force things, as you can see. So it's very interesting, actually, because we're comparing against flawed data, and we had the working theory: the better your solution is, well, in real world application, the worse the result gets, simply because they don't trust like their testing data, and we didn't either.
One thing we did is the limit on brute forcing, on submitting the data, and then we kind of hacked it, whereas we all submit at the same time. So that's why we have 100-something submissions. And one thing that really helped with the tilt was correcting like impossible values. So tilts that are too steep or too flat, we set them to a value that is more reasonable. Yeah. Do you want to add something?
In the end, our amazing Group 1, amazing orientation result is simply setting a global value and brute forcing this to like -8 degrees from south. That's it. But amazing, we won.
Similar to us, the amazing value is actually setting most the columns to 0, but a more reasonable real value was obtained, and it was about 2,600 with correct data. Yeah.
Thank you very much. All right, thank you. Big round of applause for the teams. Questions?
None.
Yes.
What's the biggest challenge over the last day for you guys?
probably Databricks. So if you install Python dependencies, so as always, so we broke the whole thing like last night for a couple hours. That was fun to debug and trace, even for the SwissScript guys. I think we all learned something. I'm not sure if we are now smarter or not. Other than that, it's really just determining if the data is good or not. Mostly it's not. And you don't trust it, like you said, like impossible angles, stuff that's, because much of the data is we have is manual entry, which means, yeah, it's not good. There are values that are obviously default values, and then in the end you would have to use some very complex solution like image processing and stuff like this. If you happen to have someone in the team that can do this, then of course that's possible. But otherwise you have to make do with what you have and what ChatGPT can do or not. And so it's also then in the end team coordination, because this is like a very sequenced issue, and we divided this into sub-problems where we could work on in parallel. But it was hard to sync, to find points where we sync and to set up the organization, because then we would have lost so much time. Well, in the end, we lost so much time because we broke the system, but you know, you learn something anyway.
All right. Oh, sorry.
I'd just like to add that one of the hardest parts was clustering the data, because we had multiple roofs for the same building, and so we had to find a way to match the roofs together for the same building. And what we did was adjacent polygons. So if you have the coordinates for each roof and you have multiple polygons and then they intersect, so we know that it's the same vicinity and the same building. Yeah.
All right, thank you. Big round of applause for the teams. Up next is challenge number 9.
Just quickly go to the... Yeah, so to remind you quickly what our challenge was, this is like showing the data again that we had as inputs, mainly meteo data and energy data, as well as historical loads, and the goal was forecast us the vertical grid load in the Swiss transmission grid for the next week, and do that for the whole year of 2023. I think everyone in our group hated me kind of when I decided yesterday in the course of the afternoon to open up an additional data set to the participants. That changed the course of their activities. Maybe may I ask our winner, Team 1, to the stage now to give us some insights. All right. So maybe I can use the time to quickly thank our data platform guys for providing this beautiful setup, this dashboard. And now, please, stage is yours.
Yep. So we attacked this challenge. Well, it was really interesting to discover the dataset and everything. And most of the magic was in feature engineering. So the datasets we used to train the models had a lot more features than the ones we were given. We used the timestamp and split it into dates and weeks, hours, etc. We added Swiss holidays, weekdays as well, and we added some lag on the weather. So basically the lag allows us to have data that sees in the past and the future. So you have additional columns that show you previous and future data. And let me just check. And we added regional data as well to the national data. And we removed, sometimes there were duplicates. There was, we don't have the data here, but for example, for the solar power, there was the same field in the national data and the regional. So we kept only the one in the regional because it's more precise. We did this with 2 other fields, with the load when we used it, and with the, I forgot the last one, the temperature, I think, yeah. And then we experimented with models, with different models, and Cat Boost is the model that had the best results in the end. And there was some experimentation also with the challenge that was proposed after. I don't know if you want to explain a bit what you tried. No. Okay. Yep.
So yeah, in the end, the idea was to, when they opened the challenge, to use the, let's say the test data, like the previous hours to help the model. We didn't have time to finish, but it seems that it helps, because I did it for a quarter and it helped, but then I have to generalize. So we have to generalize to the whole year. So yeah, didn't have time to finish, but yeah.
Yeah, so maybe when we talk about baselines here, you can see Team 1 achieved the RMSE of 722 megawatts. That comes very close to the baseline of the model that we have currently in place, so that's roughly 650. But this model is considering the data from the past, from last week, and you had to test for the whole year of 23 without having the data of 23 available for that model. So I would expect your model to actually outperform ours, but we will see about that. We will try. Questions?
Do the moderation.
My question is that we first wanted to look at the national load, but we thought that maybe when we provide more regional data with more resolution, granularity, it might help. I don't know this idea, whether it actually helped you with regional weather data, regional load data to forecast the national load. Did it help or not?
So we didn't make any comparison between the two models that you suggest, but I think from the data that we've got, of course, it helped us because it gave more information to the models, so it just performed better on the end. But you should not overfit on those new features. This is the risk.
But this is also something that we got to do afterwards to assess the regional results. That we haven't done that right now properly. So maybe you are actually gaining something there already.
But it seems it helps, sorry, because we tried a baseline yesterday with only data from the national features, and the baseline was, the error was higher than that one. So it seems it helps, but then you have to compare, like apple with apple, and to be sure that it really helped.
Thanks. More questions?
Big round of applause for the guys. So my question is, which error measure is most suitable in your problem? So if you under or overestimate, is it similarly bad, or does it make sense to weight one type of deviation more? Or for example, the maximum deviation, it matters a lot in terms of which.
That's a tough one. I would say both errors are the same, have the same impact on our models. If you overestimate or underestimate, doesn't really make a difference. We want to estimate the right load. RMSE is one version. We also use this S-Mappe, like a percentage error. This would also suit as a metric for evaluation, but except those two, I wouldn't know of any other. But to answer your question, it doesn't really matter if we over or underestimate the load. Both impacts our grid planning models that we are feeding with these data. This doesn't really answer your question, but I don't have a better answer.
Okay. In this case, thanks a lot, Malte and team, Swissgrid Team 2. So we're now, we're now switching back to the other PC laptop, and I would like to ask Laurent and Team Solarify on stage.
Thank you, Matthias. All right, I hope that everybody is still awake after so many data points. So basically, next slide. Oh, sorry. All right. There you go. Good. So, as you might remember from Ray's presentation yesterday, we were looking to actually define what we call a signature of a PV plant. And so, basically, we are not looking at the angles, the orientations of the panels themselves, but we are actually looking at the PV system as a black box. And so basically the importance for this is that we can quickly evaluate the performance of a plant. We can actually partner up with the grid suppliers, but we can also satisfy the customer consuming the energy by basically giving him a digital twin of the solar plant. And so it has also a lot of different use cases to go for a very simple response function of a solar plant, which is basically to do predictive maintenance, to do data fitting. Everybody knows that when you measure the performance of a solar plant, it is not perfect. There's a lot of errors in the measurements, also the data loggers that actually break down and just don't record anything. And so it has a lot of applications, but it also can be used as a modeling methodology to integrate the PV plant in other energy systems. So as you can imagine, this is a very simple system. It's a black box, an input and an output, and influenced by a lot of different factors. So the implementation plan that we had was we retrieve actual data from the solar plants. We combine it with coverage data, let's say from the satellites, to actually see when the cloud cover is higher and when not. And then we determine a correlation between these two, and we try to even understand how the performance of the solar plant is. And so we didn't look into anything else for machine learning and all these fancy things, just very basic stuff, understand the system as a black box. And so this is actually one of the first results, so this is a real plant, and I just pass over to Nikolai to explain this.
Yeah, sure. So what you can see here is the 12 months of the year. So as you can see, like this is like the kilowatt hours, right?
Yes.
The kilowatt hours of the plant that is getting the electricity. And so you can see like a really big variance. So this was like a first surprise result that the weather does so much influence on the PV system itself. This one? Yes. So then I was looking into how to get cloud coverage data. So what I did is I took data from Sentinel satellites. So basically I used the metadata for the satellites. When you work with satellites, you want to have pictures with 2 minutes? Okay. So when you look at satellites, you have to look if there's like cloud coverage. So I'm using basically the metadata for that satellite patch and look at how much cloud coverage there is, and I then look at that to see if that is predictive enough for the whole day as a predictor, if the PV drops. And as you can see on the left graph, you can see that it's not the best predictor, mostly because the day of the year is also very important and the time of the day. And then I did like the plot on the right side where you have where you can see it clearly, like the brighter it gets, the more cloud coverage you have. So you can see like all the bright spots are more on the bottom side and everything which is darker is on the top side. And here's like some artifact in the data where we don't know if the plant just received more panels or what happened. And here, what we wanted to try is like to do like a prediction function, which is like this KI, like a kernel function which we could use to predict the signature or like the point at the day of the year and the hour of the day. And yeah, here you can see it for one plant in 1 year. And yes, that's it.
Okay, and that's about it. So we had a great time, and I think time is up anyway. We were a small but very effective team. So thank you very much.
Questions from the audience?
Very simple question from my side. Where do you get the cloud cover data from? Is this is the same? Okay, is that like public, or is that do you have to pay for that, or how good is it? If you print a picture, is it like high resolution? What's your experience with this?
So the data is quite good. To get it, it's quite bureaucratic. So that was like the most work I did was to get that data. It's like EU data, so it feels the same, and it's basically called Stack. It's like a library. So they tried to streamline it, and when you can query this library to see for patches, so the satellite goes around the world and it visits the same patch in space like once a day about, and then you can see for that patch the cloud coverage. That is like very easy to compute there.
Thanks a lot.
It was just your secret.
Wasn't it available to get weather data? So like the actual sunshine minutes of the day for the region? Wouldn't that be like?
Yeah, I like that one more.
Okay, I understand. Thank you.
Another question? If not, thanks a lot, and I hope we'll hear in a couple of months how you implemented it and how we could use it with Solarify.
Thank you very much.
Thanks a lot. So 2 challenges left. And here with challenge number 12. The characterization of demand-side flexibility.
Hi, I will start with presenting the challenge we've got. How does this work? Okay. It's about the pilot project of Hasalu and SAK, where they send signals to devices like boilers and heat pumps to shut them off, with the overall goal to flatten like the energy load curve by putting them off when there's a huge load, and probably try to let them run when the PV runs, which is harder because they will only run when the water is cold or the house is cold. And we got a lot of data from the last 3 weeks from heat pumps and boilers. And our first challenge was to sort them. Like, we had a lot of devices who didn't really work because in summer the heat pumps won't work in the last 3 weeks. So we focused on boilers at the end. And our first part was to cluster them into 4 different groups. The first, boilers which are not running at all, which are not interesting at the end. Boiler which are bad, which misbehave, which will run even when we send the signals. The good ones with high frequency, which are this one, which are the really interesting one because we can change the load at the end. The boilers with low activity, which are also not as interesting because we can stop them from running, but most of the time they won't run anyways. There was boilers which are not running. They don't look like they're not running, but if you look at the scales, they have really low values, and this was the bad boy. We don't really know why this misbehaves, but we have to cut this boiler out from the data set.
Great, thanks. Yeah, oops, how do I go back like this? Yeah. After we found out how we had to look at the boilers in a single, we decided to put them all in a big plot. Otherwise, we had to go by them visually, boiler by boiler. So after we had them clustered in these pair plots, we started or wanted to go into a kind of characterization to figure out which groups do we have? Which, I mean, how do they behave? How much energy do they need? Over which time? How much power do they consume? How often do they go on if they have the signal to operate? And yeah, the aim is really to have 2 or 3 groups which we then can use in order to operate them in a cluster. But the question then is now, how do we operate them? And this is where the right side comes into place. The question here is, I mean, I can leave them off for 24 hours, then somehow someone will call me and say it's cold, then I have to switch them on. But this is one call too late. So we had to figure out when do we best switch them, or how much flexibility each boiler has. And this is where the right side was going. These are the 2 things which we're currently working on, and the next slides show a few more detailed insights. Yeah, go ahead.
I was hunting for data points where actually devices turned off by our signal. It was only very few. Then next. But surprisingly, I found more points when we stopped the blocking signal where devices switched on, so which give kind of a boomerang after our block period. So we actually have to take care about that.
Yeah, so this is the eventual picture. These are kind of like the 24 hours of the day, and you can see with the green marking there that the signals actually managed to reduce the load in the middle of the day hours. This is what we want, but obviously sort of a lot of the boilers then started immediately working once the signal was, the blocker was switched off, which is the red circle there, which is maybe desirable, but maybe it's also kind of like there's a more smoothing that would be needed over time.
That's it. Sorry.
Perfect, thank you. Questions for the team? Yes.
Did you calculate how much load you could produce when you turn all of them together? Could you bring down the network, or?
No. The thing is, currently they're sitting all behind different transformers. We have 26 households running, and this is what this graph here shows. The thing is, you can block them. Like if you block boilers for 24 hours, they will go on as they are just cold, right? This is thermal flexibility. So theoretically, we could then ramp them all up, but in order to mitigate this, they all have different patterns when they are operate or allowed to operate. But we never, till now, not calculated how much they would all bring if they would be all on at once. That's our but that's what you see here, and that's what we try to mitigate anyways. But yeah, correct.
What does the signal look like? Did you send to block or unblock it? How's that done technically?
Yeah. What we're doing, and this is what we are doing. The thing is, we had the pilot areas itself. They are a bit different in nature, all households, but what they all have in common is ripple control at some point, right? So what we did, we attached to ripple control. For boilers, it means we just cut off all 3 phases. So this is why I know they work, because they're just not connected to electricity anymore. And this is what we do. We send them through a protocol, and it opens up a relay, and that closes, or that's it. And then they just have no current anymore flowing through them. That's how we do it.
Thanks.
Yeah, no worries.
All right, another round of applause for the team. Oh, sorry, just one more question? No. Okay, yes, please. All right, we're slowly coming to the end. Last but definitely not least, the team number 12, Biffy.
Merci. Right, so how skyrocketing balancing prices exist. And I mean, I'm doing expectation management. Unfortunately, we were not able to find a strong pattern. But still, I want to thank a lot to the team I worked with. That's the first insight. We put a step into a rabbit hole, the balancing market or the control market, what a trip. It's super complicated, there's no low-hanging fruits, and still the team asked the hell out of me. We did a lot of plots, we tried to understand the market, we tried to see how patterns exist, we tried to backward engineer sort of how the prices come across. So we found out, for example, okay, so that's the 22nd of April, where we had a lot of PV power missing in the system. And we say, of course, tertiary energy, if the amount increases, that the Swiss grid has to buy, the prices also increases, but then in the evening, the prices also are high, but then the net imports are zero, so that means it's national tertiary energy. And to understand all this stuff was really interesting. I wouldn't claim that I still understand it, but we all made a step forward. And so the second insight is actually this. There's no low-hanging fruit to predict or to understand high balancing prices. In my opinion, the agents in the market not always behave in a rational way. And actually, and the third insight, and I'm coming to an end, is I really appreciate this platform, the Data Hackdays, because even if it's not my field of expertise, the power market, I just walk 5 steps on the one side, I can talk with Swissgrid. I do 5 steps to the other side, I can talk with Premier Energy. Then again with BKW. I mean, it's a huge potential. Come here, pose your challenge, even if it's not your field of expertise. You can learn a lot, you can talk with people, and you can maybe find some low-hanging fruits in a challenge that seemed impossible in a first sight. So, thank you.
Thanks a lot, Lucas. Hey, but it sounds like the challenge goes on. The journey, with at least with this topic, because I know, as far as I know, Matthias, he won't stop until this thing is solved.
No, he's not leaving me alone, I'm sure, yes.
Any questions to Lucas?
Not a question about the challenge, but since Lucas is on stage, Lucas, if I could give you a magic wand, which data set would you force us distribution system operators to publish?
Just one or a list?
the one that matters.
The one. I mean, we know the aggregated schedules that the Bilanzgruppen sends to Swissgrid, but to have individual schedules, that will be a big plus, of course. Yeah. Yeah.
Just on, I just want to say that we're going to also do a data expedition on energy data topics. And on the link on the project page, you can sign up if you're interested to help us get more open data sets opened up. There's been an effort over the last years to prepare data sets for Hackdays. Lucas, you did a great effort bringing these together. But we have really multiple data catalogs, a lot of data sets coming from international partners, Swiss data sets, which are very interesting on a European or international level. And we're proposing kind of a meetup format to get more of you involved in this.
So if you are interested in participating in this data exploration journey, talk with Oleg. Yes, and there's still a question, sorry.
Yeah, out of curiosity, will this experimentation or journey of understanding this balancing energy market going on, is there any work or plan to continue based on this challenge?
Not intensively. I mean, I just wanted to use the platform of the hackathon to try the idea out, but I'm aware that there's a lot of work has to be put in to conduct this challenge in a serious way. In a serious way, sorry. Yeah.
Further questions? If not, we are not 2 minutes far away from the beer. Because we reckoned we had actually 3 challenges which were pitched. Only 12 results had been presented. So I would like to take the chance also to give you a hint about another challenge. Maybe some of you, when you entered the building, on the left-hand side, you have 2 large screens showing energy clocks. Maybe you have a look on it, a closer look on it, because it's also a co-finance project with the SFOE and Energie Schweiz, supported by NCCR Automation, ETH, HSLU, with the target and the aim of making complex statistical data easy to understand. What's behind the energy system on 10, Jiri and Rafi, how many clocks do we have? 8 so far. So 8 clocks and an additional 10 are under process. So if you have 1 or 2 minutes, have a look, and this will also be the start of a small journey, I assume, because the idea is to get classes, kids, the average people who are not actually dealing with energy and the entire day, to make it easy to understand, to grab what does it mean if suddenly a nuclear power plant like BETS now, it will be shut down for 1, 2, 3 or 4 days in the overall consumption. So just have a look if you have 2 minutes of time, and then the contact person for this project is Jiri and Raphael, and herewith I would like to thank you guys. This are my last words for today, at least with the mic, and Florian, the last words for the event.
This just leaves me with 2 things. The first thing is just one small announcement, and there's also another event happening related to energy on the 29th of October. Auf dem Weg in die Energiezukunft, Innovation und ungenutzte Potenziale. So feel free to check that out. If you have questions about it, Bernie's over there. He's the man to ask. Yes, and this really just leaves me with saying thank you, merci to all of you for being here, for making this such another great edition of these Hack Days. Thanking the sponsors, all the partners that contributed, especially also the team. I've already named them on the first day, but again, a big round of applause for everyone who contributed to this event. Thank you so much, and enjoy the apéro. Enjoy, yeah?